Hello everyone, welcome to your third physics tutorial. We're going to continue talking about the description of motion, otherwise known as kinematics. Now, in the previous tutorial, we talked about and defined two very important properties of motion in addition to position. We have average velocity and average acceleration. Average velocity is going to be how much distance you cover. We're going to call that delta x. So it's going to be your final position minus your initial position, divided, so how much distance you covered, divided by how long it took you to cover that distance. Similarly, your average acceleration is how much, basically, how much your velocity changed, so your final velocity minus your initial velocity, over how long it took to make that change. And we define that as your acceleration. So intuitively, you can think of acceleration as how fast your velocity is changing, and you can think of velocity as how fast your acceleration is changing. But then we came upon the problem of having different velocities or different accelerations at different point in time. For example, let's consider yourself, so let's look at an example here. So let's say that here you are in your car and you're traveling to work. So that's a really terrible car. So here you are in your car and you're going to work. So you go here and there's a red light. Okay. So from your home, which is here, this is your home tower. Oh man, my computer's lagging a little bit. Okay, anyway, so your home is somewhere here, and you travel from your home to this red light going, I don't know, 3 meters per second. That's really slow, right? Yeah, that's really slow. 30 meters per second, I guess. Or 5 meters per second. I think that's a pretty normal speed. So if you're going 5 meters per second from here to here, that's your velocity, right? We'll call it V1. It's some velocity. And then basically you wait at this light for another velocity. In here, for a certain amount of time, you're going at 0 meters per second. And then, let's say you realize that you're late, so you speed up a little bit, and you start going at, I don't know, like 8 meters per second, until you finally get to your work. So as you can see, at different points in time, each one of these are some point in time, you're traveling at a different velocity. So, sometimes I'm interested in knowing your velocity at that instant. So right here, I want to know how fast you're traveling. In that case, it would be 5 meters per second. What if I wanted to know right here how fast you're traveling? Well, in that case, you're traveling 0 meters per second. Or right here, you're traveling 8 meters per second. So basically, the lesson to be learned here is that instantaneous velocity is not the same thing as average velocity. Because if I wanted to know on average how fast I was going, well, I would just simply take how much total distance I covered and how much total time it took me. And that will tell me on average how fast I was going, otherwise known as average velocity, which we defined in the previous tutorial. But like I said, a lot of the times we're really interested in knowing at exactly that time how fast you're going. And we call that instantaneous velocity. Now this concept transfers really similarly to instantaneous acceleration. Acceleration, as we noted in the previous tutorial, is your change in velocity. So how much your velocity changes over how long it took to change that velocity. Now, that's once again, so let's, I guess, extend this example. So let's say that when you're going from your home to that red light, you're accelerating at some acceleration. So whatever, I'm not going to choose a number, some acceleration. And then at the red light, your acceleration is it's 0. It's not change. Once you get to a velocity of 0, your velocity is not going to change for a little bit, so your acceleration is going to be 0. So you're going to be at some other acceleration. Forgot a V3 here. Okay, and then you're going to be yet at even maybe another acceleration, because This is probably not the greatest example because if you're continuously going at 8 meters per second, you're not accelerating at all. So your acceleration here is 0, and here it's 0, and here it's 0. But let's say you were accelerating, okay? So let's say you go from your home to the light at a certain acceleration, and at the light you're at a different acceleration, 0, and then you go from this acceleration to your work at a different acceleration. So clearly you have 3 different accelerations at 3 different times, 3 different points in time. And a lot of the time we're interested in knowing exactly the acceleration at that exact instant. So we call that instantaneous acceleration. So basically we have 2 new terminologies. We have instantaneous velocity and instantaneous acceleration. Instantaneous, whatever, acceleration. So your velocity at that instant in time and your acceleration at that instant in time. And basically, in order to find this out, we're going to need to use differential calculus. This work has already been done for us mathematically, we just need to learn how to use it. So to make the explanation of differentiation a little bit easier, we're going to learn about graphs and functions. So the way that we usually represent position, your position relative to somewhere. So let's say that here is our famous flagpole, and here you are, and you're moving this way. Okay, so this is going to be your position. So initially your position is here, and then it's here, and then it's here, and then it's here, etc. So your position as a function of time is changing. Now this is representing it with a diagram, but we can represent this situation using a graph or using a function. So let's go ahead and represent it using a graph. Okay. So here we have the graph. So on here, on this axis, we're going to have your time, and then here we're going to have your position. So initially, you're going to be right at the flagpole, we'll say. So initially, you're right at the flagpole, and then you keep getting further and further and farther. So you get further, and then maybe even further, and then maybe even further. So this is what it looks like. Let's say that this is the position versus time. So at this time, we'll say at 1 second you're at position 1, at 2 seconds you're at position 4, at 3 seconds you're at position 9. So we say that this is a graph of position as a function of time, or x as a function of t, because x is position. So position, when we say position as a function of time, we mean that for any time that you give, we're going to tell you the position. So that's what we say when in math you say something as a function of something else. You're saying that if you give me a value for that something else, I'll give you a value for something. Sorry if that's a really vague explanation, but this is a more concrete one. So if you give me a time, I'll give you a position. So in other words, I know where I'm going to be at every single point in time if I'm given the position as a function of time. Okay, so now we know our position at every time, or in other words, we have our position as a function of time. How can we find out this person's velocity at these different times? So basically, though, we know that the definition of velocity is basically it's the change in the x over the change in the time. So let's choose some change in the x. So let's say that we go from this x value to this x value. And how long did it take us to make that change? So to go from this x value to this x value, it took us this much time. So maybe it'll be better if I do it here. So this is my delta t, and this is my delta x. Okay. Now, as you can see, we get a slope here. So this is the slope, because delta x over delta t will give you this slope. So this slope represents graphically our velocity. So that's our velocity. Now, what happens if we make this delta t smaller and smaller and smaller and smaller and smaller? That's what differential calculus allows us to do. It makes this delta t infinitely small. So if you keep on making this delta t smaller and smaller and smaller, what happens is that you pretty much get to the point where this slope turns into a tangent. Now, the tangent to a curve, I think you know what that is. So that's basically like if you have a curve like this, the tangent at any point is going to be a line like this. Oh, my computer's frozen. Let's delete that. Okay. So differential calculus allows us to make this delta t infinitely small. Therefore, our instantaneous velocity is just a tangent to the curve. And there's a formula, there's a way for us to get the tangent to the curve. So basically, the thing you need to remember is that the tangent to the curve at that point is going to give you the velocity at that point, assuming that you have the curve of position as a function of time. So now let's write that mathematically. So we know that the velocity as a function of time is going to be the tangent of position as a function of time. And basically, whenever you're trying to find the tangent of something, it means a derivative. So it's going to be the derivative of the position as a function of time. So x prime t. This prime is how we represent derivatives. So the velocity is going to be the derivative of the position as a function of time. Now, similarly, the acceleration as a function of time it's going to be the tangent of position as a function of time, which means that it's going to be I'm sorry, the tangent of the velocity is a function of time, which means it's going to be v prime t. I'll show you guys this graphically, so don't worry too much if you're getting confused at this point. So let's say that I tell you that my position as a function of time, x of t, is going to be, I don't know, t squared, right? So I tell you that which is the case in this case actually, my position is going to be my time squared. So that really is what I drew out there. So I tell you my position is a function of time, and I want you to find out my velocity is a function of time and my acceleration is a function of time. Well, my velocity as a function of time is simply going to be the derivative of my position as a function of time. And how do I take the derivative with respect to x of this t squared? Well, you just bring down to take the derivative of a power like this, you bring down the power. So I bring down the 2, and then you write the variable, and then you subtract the 1 from the power. So 2t to the 1, which is also just 2t. So my velocity as a function of time is going to be 2t for this graph. So let's go ahead and draw that right next to it. So we'll do velocity is a function of time. It's going to have a slope of 2. It's going to go something like this. Is that a slope of 2? Yeah, roughly. I'm not drawing this to perfect scale. So velocity is a function of time, is linear. That's a linear function, and that's the slope. So it's going to be 2t. So now, as you can see, I know the instantaneous velocity because when I say velocity is a function of time, I'm saying give me any time and I'll give you the velocity. So I will tell you the velocity at that instant in time. That's instantaneous velocity. Whereas in this case, I'm saying position is a function of time. So give me any time and I'll give you a position. Now, similarly, you can find out the acceleration as a function of time by taking the derivative of the velocity with respect to time. So the derivative of this is just going to be 2. Because when you're taking the derivative of a constant, such as 2 times a variable, you simply drop the variable, and it's just going to be the constant. So let's go ahead and also graph that. So we'll also graph the acceleration as a function of time, simply 2 in this case. So it doesn't change at all. This is what we call constant acceleration, so you should keep that in mind. because it's a special case of motion. It's a very easy case of motion. And we're going to talk about this in a later tutorial. But this is going to be for the same motion, this guy moving from the flagpole away from it. So if you tell me the position as a function of time, which you did over here, you told me the position as a function of time, then you can use differential calculus to find out the velocity as a function of time and the acceleration as a function of time. Now you could also go backwards. So what if you only told me the velocity is a function of time and you wanted me to find out maybe the position as a function of time? Well, the opposite of the derivative is the integral. So let's just quickly talk about the integral. So once again, you tell me this. Let's say that you tell me my velocity as a function of time is equal to 2t. Well, I know that velocity as a function of time is a derivative of the position as a function of time, right? And what's the opposite of derivative? Well, it's integral. So the velocity as a function of time is the, let me just say, the position as a function of time is going to be the integral of the velocity with respect to time. So if I take the integral of the velocity with respect to time, integrating is the opposite of differentiating. And this is how you integrate basically a constant. So you do the opposite of differentiation. First of all, you can take out the constant. So let me write this out. Let me write this down step by step. So we need to take the integral of the v dt. Well, our v is going to be 2t dt. And that is going to be, you can take out the constant. So this is, right now I'm teaching you guys how to integrate, I guess. So take out the constant, and then you're going to be left with t dt. And then here is how you basically integrate something like a variable where it's just alone. You're going to increase, I believe you're going to increase the power since it's the opposite of deriving. So you're going to have 2, and then you're going to have t to the 2, and you're going to divide it by the new power. So now these 2's are going to cancel, and we're going to be left with t squared. And that better be our position as a function of time, which it is. So the lesson to be learned here is that if you're given any of our 3 properties, remember our 3 properties are position, so we call that x, velocity, we call that v, acceleration, we call that a. So if you're given any of these 3 as a function of time, you automatically know the other 2 by either differentiating or integrating. And in this context, we've been talking about instantaneous. So if I tell you the position is a function of time, I can, or if you tell me that, I can tell you the velocity as a function of time, the instantaneous velocity as a function of time, more precisely, and I can also tell you the acceleration as a function of time. So that's what differential and integral calculus allows us to do. It allows us to find instantaneous velocity and instantaneous acceleration. It also lets us do a lot of other cool things that we'll talk about later. So I believe that's it for, well, let's quit. I think it's a good idea to create a little summary. Okay, so basically we first talk about the difference. There's a difference between average and instantaneous. Instantaneous, anything basically tells you the value of that thing at that instant. So instantaneous velocity is going to tell you the velocity at that instant in time. Instantaneous acceleration is going to tell you the acceleration at that instant in time. So there is a difference. And in the previous tutorial, we talked about how to find the average, and in this tutorial, we talked about how to find the instantaneous. So we said that basically that velocity is going to be the rate of change of the position, so x prime t, and then we also said that the acceleration is going to be v prime t. So now we know this, and basically we can be given any of these three. We can be given position as a function of time, so we can be given position as a function of time, we can be given velocity as a function of time, or we can be given acceleration as a function of time, and we can be asked to find any of the other. So you can give me this and ask me to find this and this, or you can give me this and ask me to find this and this, or you can give me this and ask me to find this and this. So the lesson is, you can give me one of them and I know the other two automatically by either differentiating or integrating. If you give me the position as a function of time, I can differentiate once to get the velocity as a function of time, and I can differentiate a second time to get the acceleration as a function of time. On the other hand, if you give me the acceleration as a function of time, I can integrate once to get the velocity as a function of time, and I can integrate again to get the position as a function of time. So again, the important thing here is basically one key thing, that you just have to tell me one of these properties as a function of time, and I can use either differentiation or integration to find out the other two. So if you know one of them, you automatically know the other two. So thank you for watching. This is it for this tutorial, and I'll see you guys in the next tutorial. Bye-bye.